Okay, so today on the videos we were talking more about systems of differential equations, and this time we're talking more about predator-prey systems. So for the example in the video, he used robins and worms, but I assume this works for anything. So essentially the idea for like coming up with the equation was to first figure out, what happens, or the two main equations, which is like the change in the population of worms and the change of populations in the predator, the robins. So we have to find what is the population of the worms if there were no robins, which is obviously an exponential growth. So like a dWdt is equal to the coefficient times w. So that's the differential equation for exponential growth. And then for the number of robins, that's going to be exponential decay, which is going to be negative b times r, which is, b being the coefficient. And so then when you want to come up with the full system, whereas the number of worms is going to, while it's growing at the AW rate, it's also going to decrease at the rate of the worms being eaten, which is proportional to the number of robins. So for the worms equation, we end up with dW dt equals AW minus CWR. And I mean, these are kind of arbitrary variables, but like C being like a coefficient, like and so for the number of robins, that's going to increase as the increase via the worms population. So although like it's decaying, it'll also grow. And so let's see if I can screen share here. Right, so we're going to end up with, something like this when you actually graph out the differential equations, where you have like this cyclic pattern of one increasing and then decreasing repeatedly. And depending on like the certain initial populations you might have, let's see if I can find, you can have more extreme like lows and peaks and valleys and things like that. So, and then you can kind of illustrate this further if you use a a slope field, whereas you can kind of, for this one, you can see the cyclic pattern if you like trace at any point. And you can also see the higher the initial populations are, the more they'll bottom out. Yeah.
Cool. Yeah, I have some graphs I kind of want to show to just visualize the behaviors here. Um, so this is the general behavior where both functions will oscillate, but in different, but it's slightly different because of the, each of them are a slight shift, horizontal shift compared to the other. So when there are a lot of worms, robin population goes up, but as the robins eat the worms, there's less worms for the robins. So as the worm population decreases, robin population also decreases. But because the robin population decreases, more worms are able to grow, and then that goes up again. So this is the general behavior. But then we have we have these extreme cases where if the robins greatly exceed the worms, for example, here robins, it's the ratio of robins to worms is 1.3 whatever units to 0.2 worms. And in this situation, everything is just it's just a lot more vertical. Things happen a lot, it's a lot more dramatic. So robins, because there's like no worms in the beginning, the robin population is gonna like take a dive. And as the robin population decreases really fast, there are less predators for the worms, and then the worms are able to grow again. And then the worms are going to grow really, really fast. And then once there's enough worms, the robin population will start growing again as well. And then eventually, as the robin population grows, worm population decreases, and that just kind of repeats. And then there's a special situation where if the ratio of robins to worms were 1 to 1, then we would have an equilibrium solution. So then we would just get a straight line. And then, did you talk about this part?
Yeah,
Okay, cool. Yep.
but you can go into more detail if you want.
Oh yeah, this is just instead of having the rate of change of robins or worms to time, this is all about that compared to each other. So this is robins to, yeah. And then, so if we have, in a scenario where the inputs are 1 and 1, that's where we have our equilibrium solution. Otherwise, it's gonna have, there's gonna be a greater range of y values. Yep, I guess that's it.